deleted something. All right. Tonight we're going to talk about the special senses, and then we'll talk about what's on your exam next week at the end of the class. Okay. So the job of these senses we're going to talk about tonight is send information to your brain. You know that. So we need two parts. One of the lists you have to know are the receptors you use to gather the information, and then how you're going to get it to the brain. So I'm going to list the 3 types of receptors you're supposed to understand tonight. Number 1. Can anyone tell me what a photoreceptor does?
Receives light.
Receives light.
Receives light, detects light. Okay, now the hard part. What part of your body contains photoreceptors? It's on your lab because it's the eyeball. Which part of your eyeball?
Retina.
Very good. So we're going to go to the retina. Now it's got to go to your brain. How does it get to your brain from your retina?
Optic nerve.
Yeah, optic nerve, cranial nerve number 2. Very good. What part of your brain receives information from cranial nerve number 2?
Primary optic cortex. Optic cortex.
That sounds good, but let's do occipital lobe. Yes, that is true. In this class, we'll just say occipital lobe, right? So it's going to go from my eye to my brain. Now we have another receptor. This one's going to be harder. It's going to be a mechanoreceptor. Mechano means it detects what?
Pressure.
Not so much pressure. Movement or vibration. What part of your body detects vibrations? Your ear. My ears. Ear. Very good. What nerve carries information from your ear to your brain? Number 8, which is only 2 people passing next week's exam. Vestibulocochlear. Very good. What part of my brain does things like hearing,
Temporal lobe.
which is in my temporal lobe, and balance would be my cerebellum. So we'll talk about both of those today. The last one is chemoreception. Can someone tell me what you're detecting chemically? Chemicals.
Olfactory.
That's right, that's your nose. And what other part of your body detects chemicals?
Tongue.
Tongue. Very good.
Glossopharyngeal.
That's true. So now we're going to go back from my nose and tongue. So olfactory nerve and some of the glossos. What part of my brain detects things like taste and smell?
Sensory.
No.
Or insula is taste.
Actually, the parietal does not do this. Oh, you don't know? Ah, okay. The limbic system. Remind me what your limbic system's job is? Emotions. That's why the perfume industry gets you to buy it, because you remember all the thoughts with the perfume. Yes.
Is the gustatory cortex in the limbic system?
It is part of the limbic system. It activates. It's actually in the temporal lobe, but then ties in the limbic system. So we're going to learn these top 2 tonight, about those parts. So we're going to start with photoreceptors, which is on your lab quiz tomorrow, right? Let's review the eyeball. You're supposed to know the pathway to the eye. Briefly, not everything from lab. All right? Make it simple. Let's find an eyeball. I lost my eyes. Boom. Okay, so this will ring a bell for tomorrow? Yes? All right. We're going to shortcut the eye a little bit. So you do. That's not what I want. I want therapy is what I want. There. So we're going to go through and make a shorter list of the parts that we're going to focus on. We're going to start basically here and go straight back to here. So what's the very outside of your eye? Cornea. So we're going to start cornea. There's fluid behind your cornea called the aqueous humor. Very good. What comes after the aqueous humor is this big thing right here called the lens. Then there's fluid after the lens. What fluid is behind your lens?
Vitreous.
Vitreous humor. Very good. I can't spell tonight. I don't know what that is. Vitreous. That's going to hit the retina. So that's the pathway for lecture you have to know, is basic cornea to retina. But we're not quite done yet, because we have to figure out what these parts do. Oh, wrong one. Okay, so let's go through it. What's the cornea for?
Protection.
Protection, very good, that will work. So protection. There's another reason you have it. It lets light in, true. It's not the one I'm looking for, though. I know something.
Bends light.
It does. We call that a coarse focus. On your microscope, right, you have a coarse focus to help you focus. There's something on here that's going to be the fine focus. Can you guess what that would be?
Lens.
The lens. Your microscope and your eye are the same in terms of having two ways to focus, coarse and fine. So tell me what these humors do besides have neat names.
Cushion.
Partially.
Intraocular
In pressure. Bends light. These are for refraction. Refracts light, which we're not going to get too bogged down in. The retina is where the image is. This is the photoreceptor. So the photoreceptors, the things that receive the light, are in the retina after you go through this whole thing. So I'm going to stop and show you some animations of your eyeball doing its job, trying to focus light onto the retina where the photoreceptors are. So I'm going to show you a static picture first. Can I do that? All right. So here I am looking at you from far away. It goes through my cornea, all the humors, my lens, to focus on my retina. If I change my glasses and look like that, I have to do this. My lens has to fine-tune the light to keep it there. Every time I glance up and down, my eyes have to bend the light differently to keep it on the retina so you're in focus. That make sense? Remember the old days of actually having to move a lens in a camera? Does anyone still remember that? Right? You had to move the lens to keep the light on the film. Right? So I'm going to show you an animation of this. When you're bored with all that free time you have, bullshit. All right, go here. This is a guy by the name of Tutus Billis. I love his name. He didn't invent that. That's actually his name. He's a Canadian. That's okay. Right? And he has a website telling you how to do things with your senses. He has a really good website, more of the information I'm ever going to teach you. So if you're bored one night and have nothing to do, go here. Right? But he has all sorts of animations. We're going to walk through the eyeball with his. Whatever. All right, so you can do this. So here's a picture showing what my eye is supposed to do. Light's supposed to come in, gets sent to the retina. The retina converts it to a signal to my brain. Right? They're receiving the signal. Make sense? So what we're going to do is look at my lens. So in lab last week, you looked at your accommodation and all that. What you're checking is how well your lenses can focus. You have the cornea, which really doesn't move, and the lens, which does. And together, they keep the light on your retina. Let's do that. Hey, what's happening there? What are those? Those are muscles. So the lens is attached to muscles. Those are ciliary bodies you learned in lab. And when I change my focus, I have to change my lens to keep you there. So we're going to do that. So it's showing that the lens is going to change shape to keep you on the photoreceptors. So here's, with all three of your eyes, watch this thing, and this thing. Right? So the taxi cab is the picture your eye wants to send to the brain. But if your eyeball is a different shape, or your lens is not doing its job, it becomes fuzzy because you're not getting the clear picture to the retina. Right? So we did the astigmatism test in lab. That was about the shape of your eyeball. So if your eyeball's off, the image is off. I wear glasses because of that and this. So I have to focus the image better on my lens. Make sense? So the job is to keep the taxi cab right on the retina, no further back. Right? So when you get old, what happens to the muscles anywhere? They kind of fall apart, right? Life is a slow march to the grave. So as you get older, it's harder to bend your lens. So what's Grandma and Grandpa doing for the morning newspaper? They're holding it right? Because it's harder to focus and keep the image on the retina. So, let's see. I want to put a lens on you, reading glasses, so you can keep it where it belongs. This makes it worse, nothing happens. Make sense? So the whole goal of the front of the eye is to get images to the retina. Make sense? Now we're going to shift to the retina. We're going to look at this picture. And remember that your retina has different cells in it, different photoreceptors. So cones. You have cones. What's the other one called? This one over here. Rods. Over here we're going to make a chart that thou shalt know, because thou shalt know it. So we're going to make it, you can see from earlier, we have rods and with the cones. Thou shalt know the differences between them, thou shalt. So, according to this thing, cones see different what? What does it say there?
Color.
Color. So cones can do color. Therefore, tell me what rods will see. Yeah, so black and white. Some people call it gray. That's cool. Some people call it shades. That's cool. So when you're watching a black and white movie, that's what a rod is detecting, or shades of gray. Color is what cones are detecting. They see different light. Make sense? Okay. Now we're going to do light level. All right. Rods can work in dim or bright light. So can someone tell me what light level cones need?
Bright.
Bright light. So cones work in the bright, like daylight. Rods can work pretty much anytime there's light. Okay, we're going to prove that in a weird sort of way. We're going to do a little experiment. Prove I'm not making this up. So next time you're driving around Portland, looking for the greenhouse with the red door with the blue trim, and you're having a real hard time to do that, why are you having such a hard time to do that? Because when the lights go out, I don't see color, right? So we're going to prove that. Here, I'm going to try. Maybe. Okay, tell me what color I'm going to put on the board. Let's see, we're going to do this one. We're going to do this one. And we're going to do this one.
Black.
You're looking for the red house with the green door to steal the TV for your mouth. Which one are you going to see? Having a problem, aren't you?
Yeah.
Yeah. Is it better now? Right. So the minute I dim the lights, your cones can't work, so you don't know the colors. So all you can do is tell they're different shades, but you really can't see a color. Right? Every car looks dark at night, basically. Right? So that's because I'm using a different photoreceptor in my eye. Now we got to figure out where they're located. Location. I know they're in the retina. I got that. They're in the eyeball. Different spots. Cones are in the center of your retina. Anyone remember what that place was called in the center of your retina on your quiz tomorrow? The macula lutea and the fovea centralis. So we'll say the fovea. So the center of my retina has the cones. So notice all the C's, color, center. Where do you think the rods live?
Everywhere else.
Everywhere else. We'll say periphery. All right. I'm going to prove that to myself. You can try this. Okay. I'm holding up a marker. That color's purple, right? Humor me. Right. I'm going to move it to my peripheral vision, and magically now it's black. Why did it change color? Purple, black. Why is it a different color?
There's no cone.
Because there's no cones, right? So the C color, I have to look in the center of my vision. The minute it goes off center, I lose the color. It goes dim. Right? It's a bar game. Hold something up to someone's side. What color is it? Have them guess. You'll win $1. Right? I don't know. I don't know. Blue. I don't know. Blue. Right? So anything in the center, I can see color. Rods, I can't. They're peripheral. Make sense? Okay. Next difference is acuity, which means the sharpness of the vision. Which one's sharper vision, rods or cones? Cones. High acuity. If you don't like the word acuity, you can say detail. They can make out very sharp images. Rods, low acuity. Not very sharp detail. Analogy, HD TV is a cone. 80s VCR tape, dry. Right? Make sense?
Yeah.
Okay, last one we have to do is what they respond to. What activates them? Okay. Rods are temporal, looking for temporal things. That's motion. They respond to motion in the visual field. Cones are patterns in the visual field. Okay, in case you're wondering what that means, is if you see something move in your peripheral vision, the rods will turn on and notify your brain. If you look right at something, you'll see the differences in the colors and the acuity, right? So, ever have that fluorescent light flickering somewhere in your house, right? It's always in your peripheral vision and you look at it and it doesn't flicker anymore? That's this. My rods can see flickering. My cones can't see the flicker, all they can see is the pattern of the colors. So, now you understand, right? There's a fluorescent bulb in my bedroom that flickers as I'm reading a book. I keep looking at it like I'm going insane, right? Because I can't see which one it is. Because the minute I turn to look at it, I lose the flickering image, I get the pattern. So this evolved because if you're in the jungle walking down the trail, something moves in the periphery, you have to know, then you stare at it to figure out if it's a tiger or someone else. Right? So they kind of evolved for a different purpose. This is to let you know something's happening, to let you know what it is. Make sense? So when you're reading your textbook, and you want the best detail ever, you're going to have to look right at it in your bright light to get the detail and color. Right? If you look somewhere else, you'll see differences, but you won't see them in very good clarity. Make sense? Okay, so what we're going to do is we're going to show you some animations of that. All right, so we're going to go through and do our differences in rods and cones. Just kind of over here. Ready? So, on the next screen, he's showing that the same thing, when I turn off the lights, like I just did, cones don't work. So the only thing you have are rods, so you can see there's differences in shading, kind of, but you're going to have a hard time telling what color everything is because my cones do not operate that way. Make sense? The problem is I don't know how to get to the screen now. I think there. There we go. All right, so peripheral retina, rods, the fovea is cones. All right, so you have pure acuity on the outside, right? So if we go like this, oops, that was it. So this will freak you out a moment. On the left is what you actually see when the lights are on. On the right is what you see when the lights are off. Okay, so in case you think I'm crazy, let's go through this. Explain this picture. Why do I know? What does this prove to me? So daylight. Why are the colors only here?
Because your cones are only in the center.
The cones are on the center. So the only place I can see color is going to be the center of my retina. Okay, where's the better picture in the center of the periphery?
Center.
Because they're high acuity, HD. So I can see really good detail, I can see in color. As I move peripherally, I lose my color, and I lose my detail because I'm using rods, not cones. Now, explain this one. Why is that what you see driving at night?
Cones are off.
Cones are off because it's dark. So the only thing I get are rods, which see black and white only center out. Right?
Why is there a dot?
Because you can't see in the center of your vision at night. Right now, actually, you can't see me here. Really and for true. So why is not a dot like floating over my face right now? And why is when you read your textbook, why is it not like this?
Your brain kind of fill it in.
Your brain fills it in how?
Making things up.
It does make things up. What you see is what your brain wants you to see.
The usable vibes.
Right? So ever watch someone's eyes when they're reading? What do you notice about their eyes?
They move.
They jiggle, they move back and forth. That's how your brain overcomes this problem. If you just stare at the words, this would be all you'd ever see. But your brain tells your eyes to move around, and it makes the whole picture based upon what it thinks you saw on the last pass. At nighttime, your eyes are moving, so the black dot moves enough time, the brain ignores it and fills in the rest of the details. But in reality, if you held your eyes completely steady, that would be what you'd see.
Which
That
is
bother you yet?
impossible, right?
Which is really hard to do. You can't do it, right? But that's what your brain is trying to overcome by making your eyes move enough to change where you're focusing the image from the cones to the rocks. Yes.
So if you didn't learn how to see, and you got your sight as an adult, and pretend that part of your brain didn't atrophy, was that what you would see?
I don't know. I've never heard anyone ask someone blind that question.
They don't see, like, they don't have depth perception.
Cool.
There's actually been people that have had that, and that's their response, they don't have depth perception, because shadows and
Just
stuff.
flat.
Yeah.
Cool. I don't know. I guess that's pretty interesting. So two things this illustrates. One is the rods and cones. The other one is that your brain is where the image is. So you got to remember that your eyes are just cameras. They're just sending a picture to your brain. Your brain has to figure out from this what you're actually looking at. So it tells your eyes to move around and send more pictures so the brain can construct the image. Right? Okay. So if that didn't freak you out yet, let me get to the one that will freak you out at some point. How many colors do you think you can see?
3?
4. 1. It's gonna be 1.
3.
You're such a pessimist.
No, 2.
Is this any colors?
Well, okay, let's assume it's not black and white. Other than black and white, how many colors can you see?
3.
3. Okay, blue, green, and red. Those are the only 3 cones you have. So when you're looking at something, the only 3 colors your eye can detect are those 3. Blue, green, and red. But I know somewhere my wife told me what teal was, which is not one of those 3, right? Or I had to learn periwinkle, and I learned that an ivory wedding dress is not white. I had to learn it the hard way, right?
What?
Yes, I got yelled at for buying napkins that were white, and her wedding dress was ivory. So I quit buying things for the wedding. Aren't they the same? No. Right. So, how can you see colors if you can only see blue, green, and red? Where's orange on this?
Mixture of both?
It's a mixture, right? It's like Home Depot. So you have red cones firing, you have green cones firing. The brain interprets that as a yellow is a mixture of red and green to your brain. So your brain invents the colors from the 3 choices it has. So in reality, there is no yellow. Your brain invents it from a red and a green. Think about that sometime in the dark with your eyes closed, right? So that leads to the discussion. What happens if the red cones didn't work or didn't send a message? What colors would your brain be able to detect?
Blue.
So if this one was
You
gone,
would lose purple and orange.
I would lose red, orange, and some yellows. I'd have what?
Requires some
Green, some blue, some orange, right? So depending on which of the 3 colors makes it to the brain, tells the brain what color to create in your mind. So if one of them isn't returning information, the brain thinks it's not there, and so assumes it's all the other colors, right? So what do we call it when you can't see color? Now you understand the concept of color blindness. Color blindness, like this is showing, is that your brain isn't getting one of the cones or more to work, so it assumes the color is not there, because it invents it. Right? So if you're a normal person, whatever that means, right? There should be a 10 in there somewhere, right? Right? If you're colorblind, though, you can't make out that color, therefore your brain assumes it's not there, so everything is a different shade. Right? That's the logic of color blindness, is that the cones are not sending back the information to the brain to create the color. Right? 1, 3. So let's test that, right? So here are the choices for color blindness. C's. Red, green is the most common. But if you're missing the cone types, or they don't work, then you end up, your brain doesn't get that information, so the brain assumes the colors are not there, so you get a different one. So red, green is the most common, which is right here. So what color do red, green, colorblind males see?
All of them.
No.
Blue.
They can see the bluish and purples, but not reds or greens or yellows or oranges, if they're truly red, green, colorblind. Right? So what colors would a traffic light be if you're red, green, colorblind, and you can't see red, orange, yellow, or green?
Black.
They're black, right? The light comes on, the light goes off, you don't know what color it actually is. Because your brain doesn't think there's any red or green anywhere in that light. Right? Make sense? Right. So you gotta remember the brain creates the color from the information the eye sends it, yes.
Why are those the most common to not work?
It's a sex-linked gene, it's on the X chromosome, but for some reason it's a very common recessive trait. And so because it's a common recessive, to miss those two, it just happens to become the most common. I don't know if there's a specific reason why those two more than just one of the other ones. The red-green is one more common. Make sense? Yes.
How do you test, like, what colorblind you are? If you are colorblind, how do you test?
So the optician has a book that has different shades on different pictures, and depending which shade you can and can't see, will tell him which is deuteron, utan, or whatever. So instead of just knowing you're colorblind, he can actually figure out which tone or color it is, and then go from there. So you're just red, or you're just green, or whatever.
Are the cone types replaced by other cone types, so that you have just as many cones, even though
Correct.
you only see one month?
You have just many cones, but the ones just are not working or not operating. So you have still a cone there, it just doesn't send a
So your
signal.
acuity is not reduced.
Your acuity is not damaged, just the color discernment is. So you can still see, you know. So you can still read, right? You can do that, but you just can't see very well. Red apple would never work, right? So here's some math for you don't have to ever do. Your brain takes the three colors it has, breaks them into hues, adds a saturation point, and adds a brightness, and comes up with 2 million colors that you can buy at Home Depot for your bathroom. But only 3 of them are actually there. Right? Yes?
Are the 3 types of cones, is that universal in animals? Or
No.
that's-
Most colors, like most primates, they are. Birds, I think, have an extra one. Fish have some different ones. I'm not a real big on my cones, but there are variations depending on which species you're in, whether or not they have certain cones or not. Make sense? Okay, so we're gonna make this, yes.
So the species that can see ultraviolet light really well, those rods are cones.
Those are actually different.
Okay.
They're not a rod or a cone directly. I think they call it a rod, but I don't think they're the same biology. So I want you to do this experiment. Stare at the cross. Stare as hard as you can. Do not move your eyes. And tell me what you see happening. No, not that.
More purple dots. See a blue dot running the circle.
Big yellow blinking circle.
They get more bright.
Does it turn purple?
Yeah.
Stare at the
No.
white cross, and the yellow should eventually turn purple. The one's blinking.
Oh. Oh, it does.
It does. Okay, so there's 2 questions here. Why is it turning purple? I'm not doing anything. And what does that tell you? Okay, so let's figure out first why they would change color at all. If you look at the top of the screen, we're going to learn a word today. That's that word right there. So watch your cones. There you go. Oh, you big. All right. Let's learn adaptation. All adaptation means is that your nerves get tired, they fatigue. Okay? So what I had you do is I had you stare as hard as you could at the cross without moving your eyes. So your cones were basically sending impulse about these yellow circles to your brain all the time without changing. What do you think cones do if they keep getting used over and over and over? They get tired. So when they get tired, they turn off. So eventually, the cones that were getting tired began to shut off because they're getting tired, right? So I showed you a yellow dot. So the cones that respond to yellow start getting tired. Which cones respond to a yellow color or make yellow?
The red and
The
green.
red ones, right? More or less. Let's go back to that to prove I'm not making this up much. Right? Where's my yellow? So yellow is mostly red, a little bit of green. So they get tired. So if red and green start shutting off, the brain only gets information from this cone, which tells the brain you are bluish purple. Right? Because these colors quit getting sent because they got tired. This one was the only one that wasn't being used, so that comes on. that bother you yet?
Yeah.
Great.
Yes.
So in sensory adaptation, parts of your eye get tired, and so the brain gets the wrong information. It gets the information from the other cones. So again, if you stare at the X, stare at the cross, the yellow cones get tired, thereby leaving the brain only the purple one remaining, the blue one remaining. So we'll do that one more time. Maybe. The trick is you can't move your eye, because when you move your eye, the cones have a chance to recover. So you have to force your eye to stare only at the cross, which forces them to keep getting used over and over in the same location. And eventually one day, poof, here will be a purple circle.
They get tired so fast.
They do get tired very fast, which is another reason the brain keeps moving your eyes around. It's because it doesn't want them to tire, so it keeps forcing your eyes to look away. That way it doesn't do this. Right? It's sensory adaptation. All right. Another word we have to contrast that with, watch your cones, is habituation. So in habituation, the brain is ignoring the nerves. So the nerves are working, your brain just doesn't care. So in adaptation, the nerves get tired, so the brain does not get the information. But in habituation, you become a habit, the brain turns off. So I live on a farm with livestock. What do you think's in my fields, on my shoes, in the barn?
Crap.
Yeah, amen. Manure, aka crap. I never smell it. Can you guess why I never smell it? Because my brain simply ignores it, right? I mean, I smell it every day. If you came on the farm, city folk, you might freak out. This smells like a pigsty. Well, yes, it does to you. Because my brain just constantly knows it. My nose is fine, my brain simply cares. If you live next to 205, you never hear the traffic eventually, because your brain stops listening to what the ears are sending it. But this is adaptation. I'm forcing the cones to turn off, not the brain. Right? Make sense? So there's a difference in detail. One is the brain, one is the nerve. This is a nerve turning off. The brain is still listening, but the nerves are quiet.
How do you tell the difference?
Habituation normally takes longer over repeat exposure. Adaptation usually is right at the moment. And adaptation will come back the minute you look at it again, but habituation will usually not.
It's like you see your house smell.
That's right. Smokers never smell how bad they smell because of them, they don't smell, right? Because they smell all the time.
Does it have to deal with the RAS?
The RAS is part of that. So the RAS helps do that as stuff constantly from the body, the RAS sorts out. Right? Make sense? So we're adaptationing, is that even a verb? Our cones. So let's go back to this. We're going to do a little more with this. I'm going to make you more bothered, more upset. Okay? So we're going to do one more thing with some rods and cones. Okay, so you're supposed to stare at one of the fruit, just one, as hard as you can. I'm forcing you to keep your eye on one thing. Then watch what happens. What are the red apples doing? Are they turning green?
Mm-hmm.
And the green limes are turning red? And bananas are turning pink? So again, I'm not changing the color of these things. Your brain is. Because your cones are getting tired when you stare at the red apple, so the red cones get tired, shut off, leaving the green and the blue cones on. So what does the brain think? The apples must be green or blue, because the red isn't going anywhere. So if you go to wherever you shop for groceries and stare at the apple as hard as you can, it will actually turn color if you can focus on it at the exact same position all the time, which is really hard to do in the real world. Right? Again, the apple's the color your brain makes it. So when you are fighting in Home Depot, I can actually say, well, honey, it really is changing color. She doesn't believe me. Right? Okay. Make sense? So that's adaptation. So you can do the same thing this way. Start the X. What do you notice about the after images? And what color do they get? Is it the opposite color?
Mm-hmm.
Yeah, the greens go to red, the blues, yeah. Because again, you're making the cones tired that are showing up. So the other cones, which are not tired, are still firing. So the brain gets those images later. Yeah. Make sense? So that adaptation works a lot. But to overcome that, your brain constantly makes your eyes move around. So by making you focus, it forces the eyes to stay in one place. Right? So you can do that whole thing there.
So,
Yeah.
why are you seeing it after it, when your brain should be shutting it off? I mean,
There's still a residual signal. So the cones are firing, and the minute the image goes away, there's still a little bit of residual opsin there. So the brain gets that after image and it slowly goes away. The more intense the image, the longer the after image, like a light bulb in your face, stays there for a long time. So that's called bleaching. The cones fired and it takes them longer to recover. So the brain sees that as an image. So I'm going to piece this all together, which is this picture here. The taxi cab at the top. That's not what you saw. This is what you saw. Let's explain this image. Where's the color in the taxi cab? In the center where my cones are, the details in the center. Everything else is black and white and bad detail. So why is it you know the taxi cab's the upper color?
Your eyes moving
Your
around.
brain tells your eyes to keep looking at different places, and so your brain moves the cones throughout the image, remembers the colors it created, and then comes up with the picture of the taxi cab every time you stare at it. But that's actually what your brain got the lower right picture. That's what got sent to your occipital lobe. So again, your brain invents pictures from that. Pretty cool, eh? Yes. So I could screw up your life by killing off your rods and cones. I would change the information your brain gets, and therefore lead to problems like color blindness. Right? Make sense? So that's your psyche. Anyone upset now? Philosophically troubled?
So,
Yeah.
when like you can't notice changes in someone you see often, like
Yes.
someone gets their hair cut, or
Yeah.
like yesterday my roommate couldn't tell I didn't have my glasses on. Is that habituation?
That's habituation.
Okay.
I'm so used to seeing you, I don't see that you're there.
Pretty much.
Well, no, everybody brings to the right? At some point, you don't notice. You know, try remembering where like your rug is. I mean, ever do that? Like you just, what's this? We have for 10 years. I've never seen it before. Yes, you have. You walk around all the time, right? So there's a point where your brain just doesn't pay attention to anything that's not changed. So we're going to move on from eyeballs, which will bother you. We're going to go to earballs. Okay, let's do your ears, which you have not had in lab yet. But let's walk through ears.